Hi, this is Roger from Kanka Labs, and today let's talk about what a so-called reciprocal counter is, how it works, what are the advantages, and how can you implement your own with a simple microcontroller. Now, how did I come about this? I got this function generator with an integrated frequency counter and a sweep generator cheaply from eBay. But there were from the beginning a few things that annoyed me, and the first thing was that the original counter that they implemented here was built with discrete logic ICs, the old-fashioned way, just like this one here is working. And now you might already wonder now, how is it possible if we have a frequency of 10.12 Hertz that this one here is displaying 4 significant digits, this one even 6 digits, while the classical counter has only, well, basically only 1 significant digit, because in counting your last digit is always plus minus 1 count, and you can see this here. We have rounded 10.12 Hertz and it only displays 0.011 kilohertz, which translates to 11 Hertz. So not only do we have only 1 digit of valid resolution, but also the last digit is 1 count out. So, and how is it possible, although these two have both a gate time of 1 second, that here we have only 1 significant digit and here we have 6 significant digits. By the way, the little jitter here is because we have an analog function generator and there is always a little noise and the frequency is not as stable as with a quartz controlled function generator. But so 4 significant digits are completely sufficient for an analog function generator, and so it really looks like a miracle. Here you can see the gate time. It's not overflow. I've repurposed this overflow LED to a gate LED. You can see it's blinking around 5 times per second, so we have a gate time around 0.2 seconds, that we have an absolutely stable and true display. How is it possible with 200 milliseconds of gate time to get 4 significant digits of resolution at a frequency of 10 Hertz? Now let's remember how it was done back in the days when the first frequency counters came out. Mostly in the 1970s and 1980s they were built with the famous 40-pin ICs from Interseal, which had a completely integrated universal counter, were very expensive. But if you have such low frequencies like 10 Hertz, when you're gating 1 second, you only get either 10 or 11 counts during the gate time of 1 second. And so you can see the resolution is totally bad. So, and we can see the effect if we go to higher frequencies. Let's go up by around a factor of 10. Now we're already having 3 significant digits. No, it was not a factor of 10, a factor of 100. And still we're 1 digit better here in resolution than with a classical counter, which now in 1 second gets 845 or 846 counts. And here we can see 1 digit of resolution more, and here even 3 digits of resolution better than here with a classical counter. Now, if we go up to higher frequencies, then the results become better for the classical counter. But even now at 91 kilohertz, we're 1 digit better here. At the same gate time, you even can see the gate time is much faster here. Now we could change the resolution still 1 step upward. And we will see now we have 7 significant digits and here only 5. Although they have the same gate time of around 1 second. So, isn't that a bit strange? So first of all, we take a look at inside the counter here, or the function generator with the included counter, and then take a look at the schematic, how a classical counter with discrete ICs was built back in the days and what disadvantages it had. For example, because here the frequency steps are in steps of 100, they had to use even 10 seconds of gate time at the lowest range setting. That could go down to 0.1 Hertz, which is of course a period time of 10 seconds. So you have to have 10 seconds of gate time. So you're waiting, no matter what frequency you set. If you set it at the lower end of 0.1 Hertz, you only get here a 1 in the last digit. And if you go to 10 Hertz, to the upper end of the range, you have to wait 10 seconds for your display. Let's turn down it, for example, to, let's say here, something around 1 Hertz. Here we get 1.314 displayed after around 1 second of gate time. And in the original version of the counter, you had to wait 10 seconds to get a display with only only 1.3 here in the end of the display and nothing more. And you can see here, you see with 1 second of gate time, you get a display of 0, because 1 second is not enough, apparently here for this counter, to get anything displayed. While here we again have now, because I've changed the resolution, we now have 7 digits. So quite interesting, and it's a very interesting concept how to realize this, and it's quite a good example of how to utilize a microcontroller which can do all the counting stuff and all the display logic, etc. in just one single chip. So let's open this thing and first of all take a look inside how it's built up and look at the schematic of the original counting circuit. So here we are, well, not inside, but as you can see, at least half of the circuitry is implemented on the front PCB, and we'll later take a look at inside. But it's divided basically here. The left side is the digital part for the counting, and the right part is the analog frequency and sweep function generation. We'll discuss here the analog part in the next video, because there were also some annoying things that I wanted to improve, like retrofitting an logarithmic sweep generator, etc. But today it's about the counter, and you can see already here quite a lot of logic CMOS ICs, like here these 4 BCDs to 7-segment decoders and drivers, which drive the 4 7-segment LEDs or displays. And here inside, this is the area with the pre-dividers, and here was originally a GAL, a gated array logic, which is the grandfather of today's FPGAs. You can see the quartz crystal for the internal reference frequency, and they even took the effort to make a separate preamplifier, because you can use this counter also with external signals. I don't know if this makes very much use, because on the one side you need this 4-digit counter for the frequency generator, and second, who would want a 4-digit counter for any external applications? So I think they could have saved some money and some PCB space if they would have left out this and better invested this part into something more useful. Anyway, the only thing I needed to reutilize at least part of the counting ICs or of the decoding ICs, and to transfer this thing from a classical counter into a reciprocal counter is just this little 80 mega microcontroller without any additional further hardware, you only can see the quartz crystal. This switch here is for switching between frequency and period display, because sometimes it's quite useful not to have the frequency displayed, but the period. And with a microcontroller, this is of course very easily implemented. And well, the only thing else are a few bypass caps and nothing else. The LED is the gate LED parallel to the one on the front. And that's all I needed to convert this from a classical to a reciprocal counter. And of course, 2 weekends of time to do the software. But that will be we'll discuss this just in a minute. But let's take a look at the schematic, how it was done back in the days to build a classical counter with discrete logic ICs. So here we are at the schematic of the counter. Signal comes in here from the left, either from the counter or externally, and it is switched with a D-type flip-flop, which they have quite a lot of used in this thing. Then it goes through some divide by 10 counters. All in all, I can see 4 of them. It are all 74 HCMOS 4518 decade counters. So to get 4 different signals, the undivided signal then divided by 100 and by 1000. And you already can see this is the GAL, the gated array logic. And it switches here with a range switch. It not only switches the decimal point, and it switches the gate time, and it chooses the right tab of the divider chain. It also serves to light up the right range LED if it's hertz, megahertz or kilohertz. It makes the gating, and for the internal reference they have here the quartz crystal with the classical CMOS 4060 oscillator and divider, and the basic switching between counting, latching and resetting is done with also again with a decade counter with decoded outputs, the 4017 CMOS IC. We have an overflow LED, which as you can see, as you saw, I've really utilized as a gate LED because we don't have any overflow situations anymore with the reciprocal counter. And then here again we have counters which with their outputs connected to the BCD to 7-segment decoders and drivers. So loads of ICs and this special programmed gated array logic. And even though so many ICs, so many chips, this thing was in the original form not very useful. With every setting of the range switch you only had one fixed gate time, one fixed display resolution, and so this really was not fun working with this thing. And so I could reutilize here part of the decoding logic and part of the input dividers, and I could tap off nearly all of the signals here from just desoldering the gated array logic IC and using the connections and connecting them directly to the microcontroller. But now let's see how the magic works with a reciprocal counter, what it does and how you can implement it with your own code in nearly every kind of microcontroller available. So let's see how it works. As you can see, I've drawn 4 different, well, counters, timers, inputs, whatever. The signal input, that is the signal that you want to measure the frequency or period of. The reference clock, that is usually your either 10 megahertz clock if you're considering a hardware reciprocal counter, or with a microcontroller it's simply the quartz system clock. And then we have a gate timer because you usually want to have either a fixed or at least a defined gate time. And I will leave this fourth counter here open at the moment. So when your main loop, your main program says now start a new measurement cycle, the first thing it does, it will wait, that is the first step, it will wait for the first for the first rising edge after you enable the measurement cycle. And then two things have to be done. First of all, you have to take a kind of counter stamp of your reference clock. So your reference clock must be led to a timer that counts the pulses, the number of pulses from your reference clock. Now there is a nice function in Atmel microcontrollers and many others that is called the interrupt capture. What it does is when it detects a rising, or it could also be a falling edge, you can program that. Let's say if it detects a rising edge after it is enabled on the ICP input pin, the interrupt capture pin, then it will make a copy of the momentary content of the timer and copy this to a separate register so that you can save it later. You could also do an interrupt service routine which is executed when you get the first rising edge after you start your measurement cycle, and then save by hand, by software, the content of your reference clock, counter or timer. So counter and timer are here used interchangeably. So let's call this the timer value 1 at the first rising edge. Now you have to disarm or disable all the interrupts, because now you're simply waiting for your gate time to expire. So that's what the gate timer is for. It is also started when this event occurs, the first rising edge after starting your measurement cycle. So gate timer is started. These are actions 2 and 3. Make a copy of the timer content and start the gate timer. So now let's say we have a gate time of 100 milliseconds. So you want to have 10 measurements per second. It could be any value that you want, and during this time nothing else is done. All other interrupts are disabled. And now basically starts the same again. You wait for the next rising edge after your gate time has expired. This could be, of course, be anywhere. Let's say, for example, here. And then you again make a copy of your reference clock counter here. So that is again, for example, with the ICP register, or you do it manually in an interrupt service routine, and save again the timer or counter content of your reference clock, and let's call this value the timer value or timer content number 2. So now what we have is, of course, you also have to count the overflows, because if you have a 16-bit counter and a 10 or 20 megahertz clock, you will have a lot of overflows and you have to count them. But let's leave this complication out. Now what you have is already, you have a delta n, the difference between these two timer contents, which correspond each with a rising edge of your signal. Now if you would know that this is exactly one period here of your signal, we would already be ready here. But what could have happened is, what you don't know beforehand, during your gate time, your measurement time, you don't know if this is the first rising edge after this, or if there have been several counts, several cycles of your signal inputs. Here I've drawn, there are 1, 2, so this is the third rising edge. And if you don't know how many clock pulses of your signals have happened during your measurement time, your result will be wrong. And that's what the third counter is for. That is your, let's call it the signal clock counter, or simply signal counter. So you have to route your signal both to the signal counter as well to usually another pin on your microcontroller, where a rising edge will generate a capture, the capture function. So, and your signal counter is also, of course, when your measurement cycle starts, it is also initialized. Just write a 0 in it. And here we have 0 content. Here it will have 1, 2, 3. So when your measurement is finished with the first rising edge after the gate time, you also have the number of counts of pulses from your signal during the measurement time. So, and the measurement time is exactly from here to here. And let's call this M. So now what do we have? We have two values. We have the delta n, the number of reference clock pulses during this time, and we have the number of signal pulses during your gate period. And you can also see this is the minimum gate time, because let's suppose if you have 100 milliseconds minimum gate time and you would have a 1 Hertz signal, then you still would have to wait another 900 milliseconds until your first rising edge after the starting rising edge arrives. But the reciprocal counter doesn't care about this. If you just use this recipe, you will at the end have two values, the delta n, the difference of the timer content at the first rising edge and the next rising edge after your gate time has expired, and the number of clock pulses of your signal during that total measurement time. And the total measurement time is not the gate time. It's always greater than your gate time, because after your gate time has expired, you always wait for the next rising edge. So, and now it's also quite easy what's happened if you know you have delta n reference clock pulses in relation to m signal pulses. You just have to divide these two values, and the period of your signal is simply delta n divided by m. Remember, we have delta n pulses, but we have 3 signal pulses. So one signal period is simply delta n divided by m. That is all, or the frequency is just the reciprocal of that. It's m divided by m. Of course, we have left out one thing. We have to multiply this with the period of your reference clock. Well, let's take this example. We count 1, 2, 3, 4, 5, 6, 7, plus minus 1, 7 or 8 reference clock pulses and 3 clock pulses of our signal. So we would have 7 divided by 3, which gives, of course, an uneven number. But to get the period, we have to multiply this with the period of your reference clock. And if we take the reciprocal of that, the reciprocal of the reference period is simply the reference frequency, and that is all. And if we take our example here, our reference frequency would be 10 megahertz. We had counted 3 periods of our signal, 7 cycles or counts of our reference clock, and the result would be this. And the reason why this is called reciprocal counter is because of this expression here. It could also be called something else. So that is all. Your reference frequency is a known value, 10 megahertz or whatever, and you only need these 2 values. But you can see there are, in my case, there are 4 different interrupts. We have the interrupt capture interrupt. We have the gate timer, which starts and stops and defines the minimum gate period. We have the overflows here, because the Atmel's controllers only have 16-bit counters. And we can have overflows from also our signal counter, because you could, in 100 milliseconds, you could of course have 10,000 counts of your signal input, and with an 8-bit counter, and as you might know, in lower end Atmel chips you only have one 16-bit counter and 2 8-bit counters, but as you can see, this is just barely sufficient to do all the counting and all the interrupts, and you only have to count 2 things: the counts of your reference clock and the counts of your signal, and one other timer which determines when all of your measurements starts and not when it stops, but when it waits to stop with the next rising edge. So that's all. So if you like this video, please give it a big thumbs up, and see you next time with another improvement of this function generator that I showed you, and that will be a logarithmic sweep generator. So thanks for watching. Bye from Roger. Bye from Kanka Labs.